So, in this module let us understand what a reproducing kernel Hilbert space. Now, having understood the flow of ideas all the way from a vector space to the notion of normed vector space and inner product space, and then bringing this notion of convergence and then leading it towards a Hilbert space. Let us understand what a reproducing kernel Hilbert space is, because we studied these kernels as a consequence of Mercer's theorem. Okay. So, we begin with this topic of reproducing kernel Hilbert space. But before we we will, before we understand what it is in terms of reproducing property etc., which we will arrive, let us set up some definitions to start with a Mercer's kernel, considering a vector x belonging to a Hilbert space, and then any vector space of all real valued functions, and then this notion of expanding functions as a consequence of the kernel etc., and then we begin this journey. Okay. Now, consider a Mercer kernel K because kernel has to act on two vectors, right. So, I just put a dot there where x belongs to Hilbert space H and f be any vector space of all real valued functions of x generated by this kernel. So, I consider a Mercer kernel K where x belongs to this Hilbert space, and when I talk about Hilbert space, automatically it should imply to you it is a complete inner product space, and then you can compile all the details of what completeness means, what inner product means etc., from our discussions earlier. Okay. Now, suppose we pick two functions f and g from this space F, which is the inner product space, then f can be expanded as summation I equals 1 to L ai kernel acting on xi and dot. So, this dot indicates its f of x, right. I can put this placeholder as x. F of x is summation ai is a linear combination of these kernels. So, the dot indicates it is an x. Okay. So, similarly, so if I do not put an x there, it implies that you could fill in this placeholder. I can write g, this function g is a linear combination of m such kernels. So, it is summation b equals 1 to n bj kernel x j, kernel acting on 2 points x j, and this dot dot indicates x, right. So, for all xi xj tilde belonging to this Hilbert space, right. I pick two functions f and g from the inner product space that can be expanded using this kernel. And just recall from how we looked into this, kernel can also be expanded as an inner product of two vectors, right. You can express this kernel out like what we did during the SVMs, right, and you can interpret in lieu of Mercer's theorem, you can interpret them to be eigen vector and eigen value pairs, right. I mean eigen function, eigen value pairs. Okay. Now this picture is very clear in terms of expansion of this function in terms of the kernel. So we go with the bilinear form. We consider the inner product of f and g this is written as summation I equals 1 to L summation j equals 1 to n, right, because our f had L basis and g had n basis, these were the components. So we have ai bj and then we have this kernel xi xj tilde. This is the bilinear form by definition, and you can write it as a transpose some Gram matrix K times this vector. So this is the Gram matrix formed from this kernel, or you can also call this the kernel matrix. And this is my definition, right. This bilinear form is essentially my definition. And we can also write this in this form: the inner product of this kernel acting on two vectors xi, and I put a dot here indicating some vector x, with the kernel xj and that vector x, which is indicated by the dot. So this is kxi xj. This is basically one element of the Gram matrix, right. This is one element of the Gram matrix. Now let us try to rewrite the inner product slightly differently. So what I will do is as follows. I take the definition of this bilinear form, right. It is summation I equals 1 to L ai, and then I have the summation j equals 1 to n bj kernel xi xj tilde. So I consider my bilinear form. So if you see the bilinear form that I wrote, by definition. Right, this was the definition. I had a summation I equals 1 to L, summation j equals 1 to n ai bj times this kernel. So what I am trying to do, this is I am rearranging this. So ai I will pull outside the summation, I will write it in this form. Now if you carefully look into this quantity here, which is summation j equals 1 to n bj times this kernel, and if you recall the definition, of G, this is exactly G evaluated at xi. So this is basically G of xi. And what property have I used in this process? Kernel is symmetric because k xi xj tilde is k xj tilde xi because of this symmetric property. This is a very important property. Because of this property I can exchange, because if I see my original definition of G, which was here, G summation j equals 1 to n bj kernel acting on xj tilde in the first argument and any x in the second argument, and I can exchange these arguments because the kernel is symmetric. So therefore I can write the summation as the second part of the summation, which I have indicated in this red flower brace below, that is basically G of xi. So what is interesting from this is this inner product can be written as a linear combination of these function of this function G evaluated at these points xi. And this is pretty interesting, right. We started with the bilinear form of the notion of the inner product, and then we wrote it in terms of just the function G. The reader would be pretty savvy here to see that you can also express this inner product starting from the bilinear form in terms of a linear combination of functions in f evaluated over the data points, right. So you do the same math. So I will write it here. Similarly, I can write this inner product of fg as summation j equals 1 to n bj f of xj tilde. So which is sort of implying that the definition of the bilinear form is independent of how the functions f and g are represented, right. I have two different forms of representation and it is invariant to how the functions f and g are represented, and it is invariant. So it depends, it is invariant to these indices. For example, if you look at summation I equals 1 to L ai g xi, this is invariant to the changes in the index n, the coefficient vector b, and the n dimensional vector xj tilde. Likewise, when we look at this second form, which is summation j equals 1 to n bj f of xj tilde, this is invariant to L, this vector a of coefficients, and the points xi. So this is that means we have two different ways in which we can represent the bilinear forms, and we will find this these properties sort of useful. And let us list some basic properties here. The first is symmetry. For all functions f and g that belong to this inner product space, the term which is given by the inner product of f and g is symmetric. Which means I take the inner product of f and g in one way, which can be expressed as the same as inner product between g and f, and this inner product is this notion of bilinear form that I start with. So you may, if you invoke the bilinear form precisely from this definition, so if I exchange f and g in terms of my arguments, it is the same. So therefore this inner product is symmetric. We also have scaling and distribution properties. So let me state this result. For any pair of constants C and D and any set of functions f, g and h that belong to this inner product space f, the inner product of the linear combination of functions g and f, which is given by Cf plus dg with h, can be written as C times the inner product of f with h plus d times the inner product of g with h. So this is the distribution. This is a distribution property, and the scaling is if I have the constant C and D, I can pull the scalar out like the way we do with vector spaces. But I think what you have to be savvy about is, if you think about a normal inner product space in terms of vectors, you can take the inner product as, if I give you two vectors x and y, inner product of between x and y is basically x transpose y, which is same as y transpose x, right. But in this case, when we are thinking about functions and functions expressed as a linear combination using kernels, right, then I have to endow this notion of inner product using the bilinear form, and from the bilinear form I bring in these properties which should hold straightforwardly. There is another property which is the square norm property. For any real valued function f belonging to this Hilbert space, this inner product space f, for any real valued function f belonging to the inner product space f, norm f square is basically the inner product of f with itself, and you can expand this out as sum A transpose k times this vector A, and this norm is greater than or equal to 0, which implies it is non-negative definite. right. This is an important result. Last, suppose G is basically this kernel X with so G of Xi is basically kernel acting on X and Xi, that is what this dot indicates. So, what I do is I consider the inner product of a function with this kernel. Let us see what happens here. This is interesting. Now, by definition, I can express this inner product as summation I equals 1 to L. In terms of the kernel, I can expand. So, this is basically AI kernel acting on X and Xi, right. This is my f of Xi, right. I am putting this placeholder Xi here. So, this, because this can be expressed slightly differently, what I do is, because of the symmetric property of the kernel, I can write this in the form I equals 1 to L AI kernel acting on Xi in the first argument and X. So, this is nothing but f of X. So, I just retrace the steps here. This is because symmetry, which is Kx with Xi is K acting on Xi and X. So, now because I have this symmetric property, kernel acting on X with Xi is same as kernel acting on Xi with X. I have just rearranged it slightly differently, and what I have here is I get back, I write it as summation I equals 1 to L AI kernel acting on Xi and X, and this by definition is my f of X. So, what is happening here? The Mercer's kernel K can reproduce this function back. So, what I am taking is I take f of I take this function f, and I take the dot product with the kernel, right. And so, basically I take the inner product of two functions f and g, and the inner product between two functions f and g is expressed in the bilinear form. Now, I choose this function g to be the kernel acting on X, and this dot indicates it is g x I, right. So, I can think of g of x I is kernel X with x I. So, what I do is, when I express this bilinear form in the way I expand this function in terms of the kernel, using the symmetric property I get back this function. That means, the Mercer kernel reproduces this function back, and that is the reason why it is called a reproducing kernel, right. So, that is the reason why it is called a reproducing kernel, and this property is important, and it is called the reproducing kernel property. It is called the reproducing kernel property. And now this leads us into the notion of a reproducing kernel Hilbert space, right, because I take a function, this function can be expressed using a linear combination of kernels because of another function in the Hilbert space, and I choose this function to be the kernel, like the way I wrote g of some xi is kernel x comma xi, and then I look at the inner product in the bilinear form and I expand it out, I invoke the symmetry property. So what it means, I take the inner product of a function with the kernel, it gives me back the function. Okay. So let us summarize this. For every xi belonging to this Hilbert space, that means if I take a limit on this sequence, it should be contained in this space, right. For every xi belonging to this Hilbert space, the kernel x with arguments x and xi as a function of x, right, this depends on x, this kernel belongs to the space F, which is basically it is an inner product kernel, and it satisfies the reproducing property, that is I take the inner product of the function with the kernel, I get back the function, and that is very useful for me. So what this means is I start with a Mercer kernel, and this Mercer kernel is a reproducing kernel. Because if I take the inner product of two functions f and g, and this g happens to be this kernel function belonging to the inner product space f, then I can get back this function, right, by choosing this function g to be this kernel, I get back the function. So therefore the Mercer kernel is a reproducing kernel, and a reproducing kernel space which is complete implies it is a reproducing kernel Hilbert space, and that is the connection. Mercer's kernel implies it is a reproducing kernel, and I consider a reproducing kernel space which is complete in the sense of the Cauchy sense. So the convergent sequence is part of that space, right. The sequence can be function, it can be vector, whatever it is, in this case it is functions that we are dealing with, and this function, limiting function, is also part of that space. Since a Hilbert space is a complete space which is endowing an inner product space with this completeness property, and since we are bringing completeness property over a reproducing kernel space, this is a reproducing kernel Hilbert space. Okay. So this is very important. So whenever we talk about reproducing kernel Hilbert space, the following things have to be gotten into mind. First, we should understand what a Hilbert space is in terms of convergence. and being endowed with completeness property. Then we think about expanding functions in the inner product space using these kernels. Consider the bilinear form when we consider the inner product, right, and choose one of the functions in the inner product to be the kernel and which gives us back the function, right, and that is a very important property, and that is the reason why we find the use of reproducing kernel Hilbert spaces in a lot of applications. Okay. So, we have just discussed some basics. So, in the previous part of the lecture, I talked about just Cauchy sequences in terms of series convergence, etc., and then discussed what is this notion of a Hilbert space, because a Hilbert space is basically a complete space and complete inner product space, right. From those two basic ideas, we went into the notion of a reproducing kernel space and a reproducing kernel Hilbert space. So, we will stop here and then we will discuss an important result which is the representer theorem.